Did you know that the sword of a samurai owes its sharpness not just to the metal but to heat treatment? Without the right process, even the strongest steel would bend or break like a plastic. Today we will explain how heat treatments like annealing, spraying, and normalizing can completely change a metal behavior just like they did for ancient weapons and modern machines. Let's start with annealing. In this process, the metal is heated to about 700 to 900 degrees Celsius and then cooled down very slowly, usually inside the oven or put in hot sand or salt. The purpose is to soften the metal, make it more ductile, and relieve internal stress caused by cold work or deformation. Here is the microstructure of annealed steel. You can see large, uniform grains, which indicate a soft and workable material.
Next is tempering, which is done after quenching steel. Quenched steel is very hard but also very brittle, so we'll heat into an lower temperature between 105 and 600 Celsius grade, and then let it cool in air. This helps to reduce breathlessness and improve toughness. In the temperate microstructure, the martensite becomes partially decomposed, resulting in a material that keeps some hardness but is much less fragile. Now let's talk about normality. The metal is heated to a high temperature and then cooled in air faster than annealing. This produces a finer grain structure, making the metal stronger and more uniform than annealed steel. Here is the microstructure of normalized steel. Thus, this major finer grains which give better mechanical properties.
In this experiment, we wanted to demonstrate the annealing process using common iron parts and a basic home setup. The goal was to soften the metal, relieve internal stress, and observe changes in appearance and behavior. We used coarse salt because it retains heat well, allowing the metal to cool down very slowly. This simulates the slow cooling of an industrial furnace, which is critical for proper annealing. The black drywall screw reached red heat quickly because it's usually made of low-carbon steel, often with a thin phosphate coating. The nail also heated well because it's mild steel, but the silver-colored metal screw didn't glow because it likely has a higher carbon content or a surface treatment, like zinc coating or stainless alloy, that resists direct heating or reflects heat more. By leaving the metal buried in the hot salt overnight, the pieces cooled very slowly, allowing the internal crystalline structure to reorganize into larger, more relaxed grains. This reduces hardness and makes the metal more ductile, but we observe a few interesting changes. First, all the pieces looked less shiny and more gray, especially the drywall screw and the nail. Their surfaces felt rougher and drier than before. However, when we tried to bend or test the flexibility of the pieces, there was no noticeable difference. They remained just as stiff as they were before the heat treatment. This shows that even though we simulated salt with slow cooling with hot salt, the temperature of about 250 Fahrenheit or 120 Celsius was not high enough to fully perform annealing on steel.
So, our experiment helped us understand the importance of both the slow cooling and reaching the correct temperature to truly change the properties of the metal. Annealing is commonly used in industry to treat minerals before making or forming. For example, wire, sheet metal, and forged parts are annealed to prevent cracking or breakage during shaping. Each heat treatment has its specific use depending on the metal's application. Annealing softens the metal, separating reduce brittleness, and normalizing refines the structure. Thanks for watching, and we hope this video helped you understand the main characteristic and microstructure of this heat.